Welcome to all of you in this course, Thermodynamics, which is made for mechanical engineering second year, third semester students. I am Arpit Shrivastava from Mechanical Engineering Department, CSGMU Kanpur, presenting this course, Thermodynamics. Since ancient time, we are always trying to extract work from free energy. Discovery of fire is the oldest example of this approach. Today, we can see there is a lots of example in which we are getting maximum useful amount of work from free energy resources. This conversion have some basic physical concepts and some basic science, and if we want to get knowledge of these concepts, then we have to study this course thermodynamics. So let us start this course thermodynamics with some basic introduction. So this is the course. We starting this course from course content. So as I told you, this is a course for mechanical engineering second year, third semester students. This course code is ESCS 202. So in this course, firstly, we discuss about fundamental concepts, system, property, work, and heat interaction. After that, we will move towards zeroth law. Then we see first law for closed system, first law for flow process. After that, we see towards thermodynamic properties of fluid. Then we move towards second law, entropy, availability concept, equilibrium criteria, Maxwell relation, and finally, we turn towards Gibbs phase rule. Okay, so these are the contents of this course. Now we move towards introduction of thermodynamics. So we can see that thermodynamics is a combination of two words. The first one, that is thermi, and the second one, dynamics. Both words are coming to Greek language. So thermi, that is the index of heat, and dynamics, that is the index of power. So we can say this combination suggests efforts to convert heat into power. In other words, we can define the thermodynamics that it is the science of energy transfer and its effects on the properties of the system. We can define this property of the system later on in this lecture. Right now, we move towards application fields of thermodynamics. First one application is our human body. How? So we can see that our heart is continuously pumping blood towards all part of our body. Due to this circulation of blood, lots of conversion reactions are possible inside the cells, and due to these conversion reactions, cells are creating lots of energy in the form of heat, which is transferring from our body to surrounding. So if we see this condition according to weather, so in summer we want that more and more amount of heat is transferring from our body to surrounding. But in the case of winter weather, we want that heat should be stored inside our body for feeling pleasant. So for that, we wear more and more thin cloths to encapsulate this amount of heat inside our body. So how we define clothing thickness, that what thickness is enough sufficient enough to prevent heat transfer body to surrounding in the winter season. And in summer season, we wear thin clothes. So how much we reduce thickness of clothes to enhance the amount of heat which is transferring from body to surrounding in summer weather. That is depend upon the calculation of heat transfer. So this calculation is coming through with the basic concepts of thermodynamics. Okay. So second one application is heating and air conditioning system, as well as another application is conventional and nuclear power plant. So we can see these two applications with a simple example. So let us see. As all of we know that in India, we get most of the electricity power through coal fire power plant. Okay. So we know that in a power plant, there are four basic components, in which first is boiler, after that second is turbine, after that there is a condenser, and the final one there is a pump which again feed the water inside the boiler. Okay, so these are the basic components of a power plant. Okay, so see that we get heat inside the boiler through burning of fuel. If we talk about coal-fired power plant, so there is a fuel is coal, and if we talk about gas power plant, then there is a gas. So whatever we fuel, okay, so we get heat energy inside the boiler to burning of fuel. Okay, so after getting this heat, the water which is present inside the boiler getting higher pressure and temperature condition at the outlet of boiler. This higher pressure temperature condition water steam when enter inside the turbine, this steam try to rotate turbine blades, and that's why this turbine blade shaft, which is connected to electricity generator, creates power generation. Okay, and after this process, low pressure and low temperature water steam is entered into the condenser. Condenser, it is a type of heat exchanger where this heat, this water steam lost its latent heat, and this water steam is converting into again water liquid. Okay, and this water liquid which having low pressure feed inside the pump, and this pump increase again its pressure and feed inside the boiler. So this is the basic mechanism of a coal fire power plant. So if we want to design such type of power plant, then we have to decide size of this turbine as well as condenser. So how we get this size of turbine and condenser? For this decision, we have to focus that this water steam, which pressure and which temperature, how much high this pressure and temperature this water steam gaining through the burning of coal inside the cycle. So for getting this high pressure and high temperature, we have to use laws of thermodynamics. So that's why this thermodynamics plays a very important role in design purpose of power plants. Another one example of refrigeration field. So we take example of domestic refrigerator. Okay. So here again, four basic components in the cycle of domestic refrigerator. First one, there is a evaporator. Okay. And after this evaporator, there is a compressor, then condenser, then expansion device, and then again evaporator. Okay. So evaporator, that is the part of this cycle in which heat is extracted from the refrigeration cabin towards refrigerant. Okay. So in evaporator, it is transferring from refrigerator cabin to refrigerant. After getting this heat, refrigerant will convert into the vapor state because refrigerant is getting latent heat through this extraction of heating process. So after getting this latent heat, refrigerant will enter inside the compressor where this refrigerant will achieve higher pressure and higher temperature condition. Okay. So if we want to define the size of compressor in this cycle, then we have to calculate how much amount of heat is entering into the refrigerant inside the refrigerator cabin. And this amount of heat is only on calculated through thermodynamics principle. So that's why we have to learn basic concept of thermodynamics to calculate, to define, to design the power plant and refrigeration system. Okay. So these are the some basic uh, examples which is related with the application field of thermodynamics. Okay. So again, we see our slide. Yes. Okay. So these are the application. In a nuclear power plant, there is a source of heat, that is nuclear reaction. Okay. So we know what is a nuclear reaction. So in that case, we use some reflective bricks in the design of nuclear power plant, which is also based on heat transfer phenomena. So for calculation of these type of nuclear power plant, we have to again we have to again use basic principle and basic laws of thermodynamics. Next one application, that is design and analysis of automotive engine, because uh, in this type of analysis we have to calculate amount of heat which is generated in the combustion chamber through the combustion of fuel. So we have to again and again use these thermodynamics concept to calculate this heat, and again for getting cooling purpose of heat engine, getting cooling purpose of uh, other engine component parts, we have to use thermodynamics principle. Next one application, that is solar collector. This is used for solar energy power plant. And design and analysis of energy efficient homes. So first question we raise here, that what is energy efficient home? Energy efficient home are homes which have such a type of way by which we store heat in the winter season, and we transferring heat in enough amount in the summer season from home to surrounding. Okay, so in such type of energy efficient home, there is a provision of uh, fan position, air conditioning position, cooler position in such a manner that we can control heat transfer according to weather condition. So this is also depends upon thermodynamics principle and thermodynamics calculation. Okay, so these are the application field of thermodynamics. Okay, so after that we can see wait, there is some problem. Okay, yes, okay. So after that we see first important term, that is system. So question is raised here, that what is system? So system is defined as a quantity of matter or a region in a space chosen for study. Okay, we can see in this figure that a definite region in which we calculated how much pressure here, how much temperature here, how much weather condition are there. Okay, so that definite region is known as a system. If we take example, okay, suppose we are talking about a mechanical engineering department, and in mechanical engineering department there is a classroom. Okay, so if we want to measure pressure, temperature, weather, humidity level, okay, all these type of conditions inside the that classroom. So we can say that that classroom is treated like a system, treated like a system. Okay, and outside that classroom, this is called surrounding, because definition is suggesting that the mass or region outside the system is called surrounding. So everything which is lie outside the system, that is called surrounding. So beyond this classroom boundaries, everything which is lie inside the mechanical engineering department, that is called surrounding. Okay, so and another one term, that is boundary. Boundary, that is the interface between system and surrounding. Okay, that is the separation wall between system and surrounding. So boundary is defined as the real or imaginary surface that separates the system from its surrounding is called the boundary. The boundary of the system can be fixed or movable. Okay, so we can understand this line. The boundary of a system can be fixed or movable by some examples. Okay, so we see this type of example. uh, Wait, I'm trying to show some example by which you can understand this concept. Suppose we consider piston cylinder assembly. Piston cylinder assembly. Okay, so see that, that is piston, that is cylinder. Okay, sorry, and this is a piston. Okay, so what happened if there is a gas and combustion is taking place? So in that case, when this gas apply certain pressure, in that case this piston will move towards outside. So we can say this is the first condition and this is the second condition. Okay, so here what is system? System, this. Okay, and what is boundary? This is the boundary. Okay, this is the boundary, and everything which is lie outside the this assembly, this is called surrounding. Okay, so if both the walls of this piston, inlet wall and outlet wall, if both the walls are closed, so in that case this boundary, okay, these boundaries 1, 2 and 3, okay, these boundaries are fixed, but this fourth one boundary which is in the form of piston is moving. Okay, so this is the example of moving boundary, because here fourth one boundary is moving, which separate system from the surrounding. So this is the example of moving boundary. If we talk about turbine, which we use this term in the basic mechanism of power plant. So this is a turbine. Okay, in turbine, high pressure, high temperature steam is entering and exhaust low pressure, low temperature steam. Okay, so this is the mechanism. So in that case, this is the inlet wall and this is the outlet. So what happened? In this turbine case, there is always some mass is entering M1 and there is some mass M2 is exhaust from outlet wall. So there are four boundaries which separate this system from the surrounding. So there is a no motion in these boundaries, so we can say this is a fixed boundary case. We can take an example of which we have discussed in this lecture, that is classroom example. Okay, so in classroom case, all the walls are fixed, which separates system from the surrounding. So that's why it is the another example of fixed boundary case. Okay, so that's all about system and surrounding. Now we move towards type of system. Okay, so there are three types of system. First one, open system. Second one, closed system. And third one, that is isolated system. So what is open system? What is closed system? What is isolated system? We can see with another example. Okay, I am trying to show the system with examples. Okay, see, if any system, this is a system and this is surrounding. Okay, if there is a exchange of mass and there is a exchange of energy, okay, we can exchange mass as well energy from system to surrounding or surrounding to system. That is called as open system. Okay, so this is the example of open system. If we talk about practical turbine case, practical turbine, okay, so in practical turbine case, we can see that there is a some m1 mass is entering of a steam and m2 mass at the outlet of exhaust steam. And if there is a practical, this is a practical turbine, so something amount of heat surely transfer from system to surrounding. So this is the example of open system, because here mass is transferring as well as heat is also transferring from system to surrounding. Okay, another term is closed system. So what is closed system? If system is dead and surrounding, okay, if there is a exchange of heat but there is no chance of exchange of mass, so such type of system is known as closed system. Heat can transmit from system to surrounding or surrounding to system, but mass cannot be. So such type of system is known as closed system. So see this example. If there is a inlet wall and there is a outlet wall, from inlet wall fresh gasoline mixture is entering, and from outlet wall exhaust gases will emits out. But if both walls are closed and combustion of gases is taken place, so in that position when both walls are closed and gas is present inside the piston cylinder assembly. So such type of system, in this system, heat can transmit from system to surrounding, but mass cannot, because both walls are closed. So this is the example of closed system. Okay, so this is the examples of open and closed system. These are the examples. Now we move towards third type of system. This is called isolated system. Okay. So isolated system, what is isolated system? In which heat cannot transmit and mass cannot, as well as mass cannot be transmitted. Okay, so such type of system is known as isolated system. We can understand this isolated system with an example. Suppose in our solar system there is a sun and all the planets and satellites are arranged in different orbits. Okay, so if we take this solar system as a whole system, if we take this solar system as a whole system, so in that case energy is transmitted inside the system. So what happened if we take whole solar system as a system? There is a no mode that heat or mass can be transmitted from this system to out of solar system, or any mass which is entering from outside of solar system to inside of this solar system. So we can see by this example that solar system is also known as isolated system. So we can say that universe is the example of isolated system. Okay, another important thing is that system plus surrounding makes universe. Remember this, system plus surrounding makes universe. Okay, so these are the types of system which I teach you with the help of some examples. Okay, so again we move towards slides. Yes, so we can see that in open system there is a energy transfer as well as mass transfer, and example of these open system is turbine, compressor, pump, etc. And in a closed system there is a mass transfer but no, oh sorry, there is an energy transfer but there is a no provision of mass transfer, and the examples is piston cylinder device. Another isolated system, there is no energy transfer as well as mass transfer. So this is the example of these type of isolated systems are universe and well insulated thermos. The important thing is that closed system is also known as control mass system, because we already see in the case of piston cylinder assembly, if both walls are closed, mass is conserved. Okay, so that's why closed system is also known as controlled mass system, because there is no way for mass transformation. In open system, we treat open system as a controlled volume system or flow system, because there is always flowing mass from inlet to outlet wall. Okay, so these are about types of system. Now we move towards control surface. So again, we take an example of a nozzle. Nozzle is a device which increase the velocity of the flow. So we can see that here, that is a figure of nozzle, in which this is the real boundary 1, this is the real boundary 2, and this is the pipe side, and this is the exhaust side. Okay, so we can see that all the parameters of flow is changing inside the this region. So that's why we can say this region which is lie inside these boundary is called as system. Okay, so this system is separated from the surrounding by these boundary. So this is boundary 1 and boundary 2 are real, but boundary 3 and boundary 4 are imaginary, because there is no physical boundary. There is no physical boundary because this is the pipe side, but parameters will change as flow will enter inside that region. Okay, so that's why this boundary is known as imaginary boundary, and this is also known as imaginary boundary. Okay, so we can see by this example that boundary can be real or imaginary. Okay, so that's all about contour surface. Contour surface always existing inside the open system, because there is a case of, there are lots of cases of flow. Okay, next one important topic, that is properties of the system. So what is property of the system? We can relate this concept with coordinate mathematics. Coordinate mathematics, if we define any type of motion, so we will take some coordinates, x coordinate, y coordinate, z coordinate with respect to time. So suppose if any particle having coordinates x1, y1, z1 at t equals to t1, and after some some time t, when t equals to t2, particles will get different coordinates x2, y2, z2. So we can say that particle will achieve some motion which is equal to x2 minus x1, y2 minus y1, and z2 minus z1 in the interval t2 minus t1. Same type of thing is happening inside the thermodynamics. Okay, if any gas having pressure P1, volume V1, and temperature T1 at particular time T equals to T1, and after some time when T equals to T2, we will measure again pressure, temperature, and volume of that gas. We will get some readings P equals to P2, T equals to T2. So we can say that there is a something which is a change during the that time interval. So we can say that properties properties of the system is changing in this time interval. So what are the properties which define the state of the system? Like coordinate mathematics. In coordinate mathematics, we are talking about coordinates x1, x2, y1 and y2, z1 and z2. In the thermodynamics, we talk about pressure P1 to P2, temperature T1 to T2. Okay, so these are the properties which define the particular state of the system. So any characteristics of the system is called property. So there are two types of property. First one, intensive properties, and second one, extensive properties. Intensive properties, these properties are independent of the mass of the system, such as temperature, pressure and density. Okay, that is not depend upon mass. But if we talk about extensive properties, those properties whose value depends upon mass of the system, total volume, total momentum are some example of extensive properties. Okay, so that's all about properties of system. There are two types of property, intensive and extensive. Now another important point regarding intensive and extensive property, if we want to define intensive property, we use lowercase letters for representing intensive properties. But there is an exception. What? We represent pressure and temperature with capital letters. In spite of that these are intensive property. But other properties which are intensive, we represent with lowercase letters. And if we want to express extensive property, we use uppercase letters. Okay. But another exception, that mass, it is an extensive property, but we represent this with lowercase letters. Okay. All specific properties are intensive. Remember this. All specific properties. Suppose we take an example. Suppose we talk about specific volume. Okay. So volume is the extensive property. But if we talk about specific volume, what is specific volume? Volume per unit mass. Okay. So this is known as intensive property because now it is independent from the mass of the system. If we talk about a specific term, a specific volume, so it is defined as a volume per unit mass. So that's why it is independent from the mass. Okay. So like that, remember always that all specific properties are intensive properties. Okay. Now again important term, that is continuum. What is continuum? Okay. So we can understand this term with an example. I'm trying to show that example. So we talk about continuum concept. Suppose there is a chamber. In this, we feed some gas, some amount of gas. Okay. These are the atoms of gas. And this is the interatomic distance. Okay. Which is a line between two atoms of this gas, two molecules of gas. If we talk about intermolecular distance, so there is a distance between two molecules of gas. Okay. So that's all about. So if meter of molecule oblique atom of gas is less than from the intermolecular oblique interatomic distance of gas. So in that case, what happened? If diameter of molecular atom or gas is less than intermolecular or interatomic distance of gas particles, so in that case, this gap is significant. So there is the case of rarefaction. But I am talking about this later on in this lecture. But if dia of molecular oblique atom of gas is greater than distance between intermolecular, so in that case, this gap is not significant. So this is the case like that. Okay, like that. So if this is the diameter of this molecule and this is the distance, so this distance is not significant. So it is the case in which we can assume that this chamber is totally filled with gas molecules. Okay, so we can say that there is continuous nature of density will lie inside this chamber. Continuous density of gas is lie inside the chamber. So this is a called continuum concept, in which we assume that whole chamber is continuously filled with any type of gas or any type of particle. But if there is diameter of molecule or atom of gas is less than in compared to distance between these two molecules or atom, so this is the case where density of that feeding system is too much low. So we cannot assume that whole system is filled with same density throughout the container. So this is the case of rarefaction. Okay. So again we move in our slide. Okay. So they see that in the continuum, it is a very convenient to disregard the atomic nature of a substance and view it is as a continuous, homogeneous matter with no holes. This is a continuum. And the continuum idealization allows us to treat property as a point function and to assume that properties vary continually in a space with no jump discontinuities. Okay. But in the case of rarefied gas flow theory, at very high vacuum or at very high elevation, the mean free path may become large, and for such case, the rarefied gas flow theory should be used. Okay, so in thermodynamics, we use this continuum concept only because we read classical thermodynamics. Okay, in statistical thermodynamics, we use rarefied gas flow theory, which is beyond our course content. Okay, so this is all about continuum and rarefied flow theory. Okay, now we move. So another point is state. What is a state? So we defined this term in previous, that at a given state, all the properties of the system have fixed value. If the value of even one property change, the state will change to a different. Suppose we take two examples. There is a stage A and another stage is B. We have some gas inside the this piston cylinder assembly, which have mass m equals to 2 kg, temperature 20 degrees centigrade, and volume 1.5 meter cube. After some time, we check that mass is same, that is 2 kg, but temperature is changing now. That temperature is T2, that is almost about 20 degrees centigrade. No, T2 is also same, but volume is changed. Here V1 is 1.5 meter cube, but in the second case, V2 will become 2.5 meter cube. So that's why there is a change of volume, but T1 and T2, M1 and M2, these are same, but still we can say state is changed because one property is changed. Okay, so this definition is suggests that at a given state, all the properties of the system have fixed value. If the value of even one property change, in this example, we can see that V1 is changing. V1 is changing from V1 to V2, that is 1.5 to 2.5, irrespective that mass and temperature are constant. Okay, so this is the defined state. So we can say state is just like a coordinate. In coordinate geometry, we define motion with the help of coordinates x, y, and z. So same thing is happening inside the thermodynamics. We define a state with the help of properties of the system. Okay, so that's all about. Now we define equilibrium. The word equilibrium implies a state of balance. In an equilibrium state, there are no unbalanced potentials or driving force within the system. A system in equilibrium experiences no changes when it is isolated from its surrounding. That means there is no change. States becomes constant when system is lie under the equilibrium. Okay, so that's all about equilibrium state. So now we talk about thermodynamic equilibrium. What is thermodynamic equilibrium? So thermodynamic equilibrium, if and only if relevant when these three types of equilibrium is are existing. These three types of equilibrium. First one, that is thermal equilibrium, in which temperature is the same throughout the entire system. Okay. Second one, that is mechanical equilibrium, in which pressure of the system is constant throughout, because we know that pressure, that is the index of force, which is defined as force per unit area. If pressure is a constant as well as area of cross section is a constant, then we can say that there is a forces are also constant. Your forces is maintaining same value in throughout the system. And the third one, that is chemical equilibrium. A system is in chemical equilibrium if its chemical composition does not change with time. That is, no chemical reaction occur. That means rate of forward reaction, that is equal to rate of backward reaction. That means there is no concentration change in product as well as in the reactant. Okay. So that's all about types of equilibrium. So when these three types of equilibrium are happening, then we can say that thermodynamic equilibrium is lying inside the system. Okay, so remaining fundamental concepts of these thermodynamic system we will discuss in upcoming lecture. Okay, so in upcoming lecture we discuss about cycles, about quasi-static processes, and some take practical fundamental examples which is related with these concepts, which make a big building of different engineering applications. Okay, thank you very much.